Have you ever, stopped and wondered why cut grass smells the way it does? Or, how medicine works? How does it know where to go in your body? It seems kind of magical, but the answers, well, they're all down at the molecular level. It's about how atoms connect, the shapes they make, and how those shapes dictate, well, pretty much everything. So today we're doing a deep dive into molecular geometry, those intermolecular forces, and the theories behind chemical bonding. The goal is really to give you a clear path to understanding this invisible architecture.
It really is fundamental, isn't it? How the big stuff we see and interact with is all governed by these tiny, tiny rules.
Hmm.
And understanding these theories, it lets us predict why water is wet, basically, why it's liquid at room temperature when something like oxygen is a gas. It's the foundation.
Okay, let's get into it. First stop, molecular geometry, the blueprint. And we have to start with VSPR, right? Valence shell electron pair repulsion. It sounds complicated, but the core idea is actually pretty simple. Electrons in the outer shell, the valence shell, push each other away, they repel, so they naturally arrange themselves to be as far apart as possible, like tying balloons together at the center. They just spread out, don't they?
Exactly that. The balloon analogy is perfect. And the key is thinking about electron domains. That's the term we use. It's not just lone pairs or single bonds. A single bond, a double bond, even a triple bond. Each counts as only one electron domain because it occupies one region of space, you see.
Ah, okay, that's important because it leads to this distinction, doesn't it, between electron domain geometry and molecular geometry. Electron domain geometry is like the arrangement of everything, bonds and lone pairs. But molecular geometry is only where the atoms are. And they're not always the same thing.
Precisely. Especially when lone pairs get involved. They influence a shape, but they aren't part of the final molecular shape description. So let's run through the basics. 2 electron domains, that's linear, think CO2, 180 degrees, easy. 3 domains gives you trigonal planar, flat, like a triangle. BF3 is a good example, 120 degrees between bonds. 4 domains is tetrahedral. Methane, CH4 is the classic, those 109.5 degree angles. That gets a bit more complex. 5 domains, you get trigonal by pyramidal, like PCl5. It has different positions, axial and equatorial. And 6 domains gives you octahedral. SF6 is a common one. All 90-degree angles between adjacent bonds.
Okay, so those are the ideal shapes. But here's where it gets really interesting, I think. They aren't always perfect, are they? Those angles can be slightly off. And you mentioned lone pairs influencing things. Is that why?
That's exactly why. Lone pairs are, well, they're a bit bulkier electronically. They occupy more space around the central atom than a bonding pair does. So they push the bonding pairs closer together. Think of ammonia, NH3. It has 4 electron domains, 3 bonds, 1 lone pair. So the electron domain geometry is tetrahedral. But that lone pair squeezes the HNH bonds. Instead of 109.5 degrees, the angle is more like 107 degrees.
Okay, so the lone pair repulsion is stronger. What about double or triple bonds?
Same idea, really.
Yeah.
Multiple bonds have more electron density concentrated between the 2 atoms, so they also repel more strongly than single bonds. You see this in molecules like, say, acetic acid. Around the carbon that's double bonded to oxygen, the angles will be slightly distorted from the ideal trigonal planar 120 degrees.
Right. And if you have a bigger molecule like methanol or that acetic acid you mentioned with more than one central atom.
You just apply VSEP to each central atom one by one. Look at the first carbon in methanol, figure out its geometry. Then look at the oxygen, figure out its geometry. You break it down piece by piece. It's very systematic.
Okay, that makes sense. So we've got these shapes. But why do they matter? What's the consequence of a molecule being linear versus bent or tetrahedral?
Well, that leads directly to molecular polarity. The shape is absolutely crucial for determining if a molecule overall has a positive end and a negative end, a dipole moment. And that polarity influences almost everything: physical properties, chemical reactivity, even biological function.
So for just 2 atoms, it's easy, right? Different atoms, different pull-on electrons, usually polar.
Usually, yeah, if the electronegativity difference is significant. But with 3 or more atoms, it's about the sum of the effects. You need to consider both the polarity of the individual bonds and the molecule's overall shape.
Like vector addition, where direction matters.
Exactly like vector addition. Each polar bond is a vector pointing from the less electronegative to the more electronegative atom. You add up those vectors. If the molecule is symmetrical, those vectors might just cancel each other out.
Like in CO2, the CO bonds are definitely polar. Oxygen pulls hard.
Very polar bonds. But the molecule is linear, so you have one vector pointing left, one pointing right, equal strength. They cancel perfectly. CO2 is nonpolar overall.
But water, H2O, same idea. 2 identical bonds to oxygen, but it's bent.
Right. Thanks to those lone pairs on oxygen, the shape is bent. So the bond dipoles, the vectors, don't point in opposite directions. They add up, giving water a significant overall dipole moment. Water is very polar.
Okay, so geometry is key. What about something like carbon tetrachloride, CCl4, tetrahedral?
Tetrahedral, yes. And each CCl bond is polar. But because it's perfectly tetrahedral, the four bond dipoles point symmetrically outwards and cancel each other out. CCl4 is nonpolar.
But if you swap one chlorine for a hydrogen, like in chloroform, CHCl3.
Ah, now the symmetry is broken. The CH bond polarity is very different from CCl. The vectors don't cancel anymore. Chloroform is polar.
That's cool. And you can even use this to tell isomers apart, right? Same formula, different structure.
Absolutely. Take cis and trans-dichloroethylene, C2H2Cl2. In the cis isomer, both chlorines are on the same side of the double bond. The bond dipoles add up, making it polar. In the trans isomer, the chlorines are on opposite sides. The bond dipoles cancel out. It's nonpolar. Same atoms, totally different polarity, just because of the arrangement.
Wow. Okay, so shape determines polarity, and polarity then determines how molecules interact with each other.
Precisely. That brings us to intermolecular forces, or IMFs. These are the attractions between molecules, not the bonds within them. They're weaker than covalent or ionic bonds, much weaker, but they're the reason substances condense into liquids and solids. They dictate boiling points, melting points, viscosity, all sorts of physical properties. They're like molecular stickiness.
Okay, let's break down the types of stickiness. First up, dipole-dipole. Sounds straightforward.
It is. It happens between polar molecules. The positive end of one molecule is attracted to the negative end of its neighbor. Simple electrostatic attraction. The more polar the molecule, the stronger this force.
Got it. Then there's the famous one, hydrogen bonding. Is it actually a bond?
Not really a true bond like a covalent bond, despite the name. It's a super strong type of dipole interaction. Very specific. It only happens when hydrogen is bonded directly to a small, very electronegative atom. Specifically, nitrogen, oxygen, or fluorine. N, O, or F.
Okay, why those three? And why is it so strong?
Because N, O, and F are so electronegative, they pull the bonding electrons so strongly away from hydrogen that the hydrogen nucleus, the proton, is left almost bare. It creates a really concentrated, intense, partial positive charge on the hydrogen. This highly positive hydrogen is then strongly attracted to a lone pair on the N, O, or F of a neighboring molecule. That's the hydrogen bond.
And that explains those weirdly high boiling points for water, ammonia, HF.
Exactly. Compared to other similar hydrides like H2S or PH3, their boiling points are way off the charts. It's all because of that strong hydrogen bonding holding the molecules together much more tightly in the liquid phase.
Okay, what about nonpolar molecules? They still condense, right? So they must attract each other somehow.
They do. And that's thanks to dispersion forces, also called London dispersion forces. These are present in all molecules, polar or nonpolar, but they're the only IMF for nonpolar ones. They're caused by the random movement of electrons. For an instant, the electrons might happen to be more on one side of the molecule, creating a temporary, instantaneous dipole.
Like a fleeting wobble in the electron cloud.
Exactly. And that temporary dipole can then induce a similar temporary dipole in a neighboring molecule. This leads to a weak, short-lived attraction.
So they're always flickering in and out of existence.
Pretty much. But they add up. And their strength depends heavily on the molecule's size and shape, specifically its polarizability. Larger molecules with more electrons spread over a larger area have electron clouds that are more easily distorted, more polarizable. This means stronger dispersion forces.
Ah, like the halogens. F2 and Cl2 are gases, Br2 is liquid, I2 is solid, they get bigger.
More electrons, more polarizable, stronger dispersion forces, higher boiling points. It's a perfect trend, showing the importance of these forces.
Okay. And you mentioned one more, ion dipole.
Right, briefly. That's the attraction between an ion, like Na plus or Cl, and a polar molecule, like water. It's what happens when salts dissolve in water. The positive ion is attracted to the negative end of water, the oxygen, and the negative ion is attracted to the positive end, the hydrogens. These are generally the strongest IMFs we're talking about today.
So ranking them roughly. Dispersion is weakest but universal. Then dipole for polar molecules, then hydrogen bonding as a special strong case, and ion dipole is the strongest interaction with ions.
That's a good summary. And understanding which forces are present and how strong they are is absolutely crucial for explaining why stuff is solid, liquid, or gas under certain conditions.
Okay, this is great, but Lewis structures and VSEPR, they're powerful, but they don't explain everything, do they? Like, why do bonds even form, or why are some bonds stronger than others?
Right. They're descriptive models, but they don't get into the quantum mechanical why. For that, we need better bonding theories. The first step beyond Lewis is valence bond theory, or VBT. VBT pictures a covalent bond forming when atomic orbitals on adjacent atoms overlap. Critically, each orbital involved in the overlap usually contains one unpaired electron, and their spins must be opposite.
So the electrons are shared in that region of overlap.
Essentially, yes. The overlap allows the electrons to be attracted to both nuclei simultaneously, which lowers the potential energy and makes a molecule more stable than the separate atoms. So in H2, you have the overlap of two spherical 1s orbitals. In F2, it might be the end-on overlap of two 2p orbitals. In HF, it's the overlap of hydrogen's 1s and fluorine's 2p.
Okay, and VBT also explains why bonds point in certain directions, right? Like in H2S, you mentioned the angle was about 92 degrees.
Yes, VBT handles directionality. Since p orbitals are oriented along the x, y, and z axes, perpendicular to each other, the overlap of, say, two of sulfur's 3p orbitals with hydrogen's 1s orbitals would naturally lead to a bond angle around 90 degrees, which matches H2S pretty well.
VBT has problems too, doesn't it? You mentioned BCl2 earlier. Beryllium's ground state electron configuration is 1 has 47 senses, no unpaired electrons. How does it form two bonds?
Exactly, and methane CH4. Carbon's ground state has two unpaired electrons in 2p orbitals. VBT would predict CH2 with a 90-degree angle. But we know methane is CH4 with 109.5-degree angles. VBT, in its simplest form, can't explain these common molecules.
So we need to upgrade VBT.
We need to enhance it, and that enhancement is hybridization. It's not a totally new theory, but an essential part of VBT for explaining molecular geometries. The idea is that before bonding, the atom's valence atomic orbitals, like S and P, can mathematically mix together to form a new set of degenerate hybrid orbitals. These hybrid orbitals have shapes and orientations that match the observed geometry predicted by VSEPR.
So the atom rearranges its orbitals to make better bonds, like blending them.
That's a good way to put it, an orbital blender. For linear geometry, two electron domains, like in BeSiL2, one s and one p orbital mix to form two sp hybrid orbitals. They point 180 degrees apart. For trigonal planar, three domains, like BF3, one s and two p orbitals mix to form three sp2 hybrid orbitals, pointing 120 degrees apart. And for tetrahedral, four domains, like CH4, 1s and 3p orbitals mix to form four identical sp3 hybrid orbitals, pointing 109.5 degrees apart toward the corners of a tetrahedron.
And for atoms like beryllium or carbon, they might need to, promote an electron first to get enough unpaired electrons before they hybridize?
Correct. Often we invoke electron promotion, like from 2s to 2p in carbon, followed by hybridization to get the right number of orbitals ready for bonding. The energy cost of promotion is paid back by forming more, stronger bonds. And for elements in the third row and below, they can even involve d orbitals in hybridization to accommodate more than 4 electron domains, leading to sp3d2, octahedral hybridizations.
Okay, hybridization explains the shapes. What about double and triple bonds? How does VBT handle those with hybrid orbitals?
Great question. This introduces two types of bond overlap, sigma bonds and pi bonds. Sigma bonds are formed by the direct, head-on overlap of orbitals, hybrid or atomic, along the line connecting the two nuclei. All single bonds are sigma bonds. Sigma bonds allow free rotation around the bond axis.
Okay, head-on overlap. What's pi then?
Pi bonds result from the sideways overlap of unhybridized p orbitals. These p orbitals are parallel to each other and perpendicular to the internuclear axis. You only get pi bonds after a sigma bond has formed. So a double bond consists of one sigma bond from hybrid orbital overlap and one pi bond from sideways p orbital overlap.
Like in ethylene C2H4, the carbons are sp2 hybridized.
Exactly. Each carbon in ethylene is sp2 hybridized. They form a sigma bond between them using sp2-sp2 overlap. The remaining sp2 orbitals bond to hydrogens. Each carbon also has one unhybridized p orbital sticking out, perpendicular to the molecular plane. These two p orbitals overlap sideways to form the pi bond.
And that sideways overlap, that's what stops the molecule from rotating freely around the double bond, creating those cis-trans isomers we talked about.
Precisely. Rotation would require breaking the pi bond, which costs energy, and a triple bond. That's just taking it one step further. Like in acetylene, C2H2, the carbons are sp hybridized. They form a sigma bond, sp-p overlap. Then there are two pairs of unhybridized p orbitals, one pair on the axis, one along the z-axis, that overlap sideways, forming two pi bonds. So a triple bond is one sigma plus two pi bonds.
Wow, okay. VBT with hybridization and sigma-pi bonds seems really powerful. Does it explain everything?
Almost.
Wow.
But not quite. Remember oxygen O2? VBT, even with hybridization, predicts it should be diamagnetic, all electrons paired. But experiments clearly show O2 is paramagnetic. It has unpaired electrons and is drawn to a magnetic field. VBT fails here.
So we need yet another theory.
We need a more sophisticated one, yes. And that's molecular orbital MO theory. It takes a fundamentally different approach. Instead of orbitals belonging to individual atoms and overlapping, MO theory considers orbitals that belong to the entire molecule. Atomic orbitals combine, mathematically, to form a new set of molecular orbitals.
So the electrons aren't just localized between two atoms anymore. They're spread across the whole molecule in these MOs.
That's the core idea. And just like atomic orbitals, these molecular orbitals have specific energy levels and shapes, and each can hold two electrons with opposite spins. An important rule: the number of MOs formed always equals the number of atomic orbitals combined. When atomic orbitals combine, they can do so constructively, forming a lower energy bonding molecular orbital, which stabilizes the molecule, or they can combine destructively, forming a higher energy antibonding molecular orbital, often marked with a star, which destabilizes the molecule.
Lower energy is good, higher energy is bad, basically.
Pretty much. Electrons in bonding MOs pull the nuclei together, while electrons in antibonding MOs pull them apart or occupy space outside the internuclear region. We draw MO energy level diagrams, showing the relative energies of the atomic orbitals and the resulting bonding and antibonding molecular orbitals. We fill these MOs with the molecule's total valence electrons, starting from the lowest energy level, following Hund's rule and the Pauli principle.
And from this diagram, you can figure things out, like stability.
Yes, we calculate the bond order. It's number of electrons in bonding MOs, number of electrons in antibonding MOs divided by 2. A bond order of 1 corresponds to a single bond, 2 to a double bond, 3 to a triple bond. A bond order of 0 means the molecule is unstable and likely doesn't exist, like He2.
Okay, so how does this explain oxygen's magnetism?
Ah, the payoff. When you construct the MO diagram for O2 and fill it with its valence electrons, you find that the highest occupied molecular orbitals, which are antibonding pi orbitals, each contain 1 electron and they have the same spin, following Hund's rule. 2 unpaired electrons. MO theory correctly predicts O2 is paramagnetic where VBT failed. It also correctly predicts N2 with a bond order of 3 is diamagnetic, all electrons paired. It's incredibly powerful for predicting these properties.
So it seems like we have a whole toolkit of theories: Lewis, VSEPR, VBT with hybridization, and MO theory.
Exactly. And none of them is the single true way molecules bond. They're models, each useful for different things. Lewis is great for quick electron counting. VSEPR is fantastic for predicting shapes. VB hybridization gives a good picture of localized bonds and geometry. MO theory is best for understanding magnetism, electron spectroscopy, and situations where electrons aren't neatly localized.
So what does this all mean for understanding really complex molecules? Do you just pick one theory?
Often, the best description comes from combining them, especially when you encounter molecules that need resonance structures in Lewis theory, like benzene, C6H6, or the carbonate ion, CO32. This points towards delocalized bonding.
Delocalized, meaning the electrons aren't stuck between just two atoms.
Precisely. They're spread out, shared across multiple atoms. For benzene, the best picture uses VB hybridization to describe the sigma framework. Each carbon is sp2 hybridized, forming single sigma bonds in a hexagonal ring, and to the hydrogens. But then, each carbon also has an unhybridized p orbital perpendicular to the ring. These 6 p orbitals overlap sideways all around the ring, forming delocalized pi molecular orbitals that extend above and below the entire ring. The pi electrons aren't stuck in free double bonds. They're shared equally around the whole thing.
Like an electron highway above and below the ring.
That's a perfect analogy. That delocalized pi system explains benzene's stability and why all its carbon-carbon bonds are identical in length, intermediate between typical single and double bonds.
Wow. Okay. So we've gone from simple electron repulsion dictating shape to orbital overlap, hybridization, sigma, and pi bonds, and finally to these molecule-wide molecular orbitals and delocalization. It's quite a journey into the unseen.
It really is. And understanding this journey, this framework, isn't just academic. It's the absolute foundation for predicting how substances will behave, how reactions will occur, and even how we can design new materials.
Which brings us to a final thought, maybe.
Yes. Consider this. Now that you understand these underlying principles, shape, polarity, intermolecular forces, the nature of bonding, how does this empower scientists? How does knowing about these invisible structures and forces allow chemists, material scientists, pharmacologists to actually design new molecules? Molecules with specific functions, whether it's a drug that fits perfectly into a biological target, a new type of plastic, or a better catalyst. Think about the power that comes from understanding and being able to predict and ultimately control this unseen molecular world.